just quadrature scheme. And then we also looked upon Gauss quadrature scheme. So what we showed was last time an integral of v of x dx with certain intervals, not necessarily a -1 to dx, can be obtained as sum of where v of I is v of xi. So we showed that Simpson trapezoidal rule is order of h square. This is order of h to the power of pi, order of h to the power of n minus 1, and this is order of 2n minus 1. That means if you use trapezoidal rule, you can integrate exactly up to a quadratic polynomial. This is, you can do it up to quadratic polynomial. This is n minus 1th polynomial. This is 2n minus 1th polynomial. The only difference is between have n-point quadrature, n-point Gauss quadrature will still do 2n minus 1. That is, it takes extra duty effort to with the same number of computings. This will have up to higher degree polynomial exactly integrated. Okay, and this weights and the corresponding xi's are both variables in the Gauss quadrature schemes, and we have shown that for 1-point Gauss quadrature scheme. So for 1 point, it is xi is equals to 0, wi is equals to 2. For 2-point, we showed that xi is equals to plus or minus 0.577 and wi is equals to 1 each. And similarly, the other higher points are also shown: 3-point Gauss quadrature scheme, 4-point quadrature scheme, and so on. And we also showed that how to obtain our Gauss quadrature scheme points, n-point normal quadrature scheme points using a matrix method. And similar methodology can also be used to determine both the positions as well as the weights for the n-point Gauss quadrature scheme, so using the test polynomials, which has to be integrated exactly. So that is what we have reviewed in the previous week. And with this, all the things that are part of a finite element of elastostatics is completely defined up to this point. So now at this point it is more I mean, we are in a very good position to look into actual implementation of a finite element code. So for that reason, what I would suggest is everybody to go through this website .solid mechanics. It's a continuous solid .org by Professor Alan Power at Brown University. So he has his website in which the chapter 8 deals with both FEM and advanced FEM, but we restrict ourselves to FEM. Advanced FEM like hyperelasticity, hypoelasticity, viscoplasticity, all that things comes under the advanced finite element. But the basic finite element are all dealt in this thing, so look into those things. And he has also a code section which I'll show you, and those codes I will try to show you and implement you in today's lecture. And it happens that Professor Alan Bauer is my PhD advisor, and we look into his codes to kind of see how all the things that we learned throughout this course are used to solve problems of bigger scale using a MATLAB coding. For that, you should all have some MATLAB, or you can go and have a trial license. So what I will do is I will show the MATLAB with me, and we will run through those codes. So So let me just, so we will go, today our things would be codes. So what I will do is I will first show you his website from where we are obtaining these codes. So go to solidmechanics.org website, and this is the Alan Bauer's website, and in the table of contents you can see chapter 8 with linear elasticity, statics. This is for dynamics, and hypoelasticity. These are the advanced topics. You don't have to worry about it. So what we mostly covered is this part of it in this course in a different manner, in much more elaborate manner. But what I want to emphasize is you to go through his FEA codes, come to the MATLAB section, and let us review this 1D static code. So once you download this, let me open his code. So this is 1D finite element code in which we will show how to code a given element, a bar element with given a length of 5 and shear modulus of 50 and Poisson's ratio of 0.3 and body force of 10 and traction of 2 is set up, and total number of elements in this case is 3, and hence the number of nodes would be accordingly shooted up. So let me show you the see, in this case, what he's calculating is the displacement of a 1D bar when it is subjected to uniform force and when its left end is constrained, that is at x is equals to 0, u is equals to 0, and at x is equals to L, a prescribed traction has been imposed. So this would look something like this. it is subjected to traction at x is equals to L. So x is measured from these things. It has its Young's modulus E, Poisson's ratio nu, and cross-sectional area A, and this, in the finite element sense, is modeled as a line element. When we take number of elements as 3, this is number of elements as 3. Okay, so here, okay, let me explain it. So the total number of nodes he has chosen is, in this case, is supposed to be 10. So so L is equals to 10 is the number of elements, and NE is type of the element. If NE is equals to 2, it is an element is a two-noded element, and if NE is equals to 3, it is a three-noded element. So here x is equals to 0, and this is x is equals to length. So L refers to the total number of elements in his code. So that is how he has discretized, and accordingly the coordinates has been calculated by setting up each element is of equal length. That's right. So the total number of nodes, let's say in this case, let's make this one as two-noded element. So nodes on each element, either 2 for a linear element, 3 for the quadratic, and then accordingly the coordinates will be set it up. And once the coordinates is set up, then based on this is for the linear element, since we have chosen, it will set up your connectivity table, and once the integration points, so depending upon, since it is we have used NE is equals to 2, we'll get number of integration points would be NE minus 1. So in our case it will get us 1 point integration scheme. So this will be invoked. Once you have this one endpoint thing, now you are ready to get your global stiffness matrix by getting the element stiffness matrix for all the elements. So now you run over 1 to all the elements and get its local coordinates, develop its element stiffness matrix, and once you have element stiffness matrix, you assemble them and obtain the global force vector. Once the global force vector is also obtained, then you impose the traction boundary conditions. Once the traction boundary conditions are done, then you are applying your kinematic boundary conditions. Once the kinematic boundary conditions are there, now the K matrix is no more singular, and you can solve those things by inversion. And he is using LU decomposition. Once you know the displacement, then the displacement is plotted. So this is what is there. It's a simple code. So let me run through it for your benefit. This is the length of the bar. Is the cross section. Nu is the shear modulus. Nu is the Poisson's ratio, and this is body force and tractional forces. This is total number of elements. This is number of nodes per element. That will give total number of nodes, and the nodal coordinates are generated by equipartitioning them. So, and then accordingly the connectivity is measured or made. So this connectivity table is useful in setting up your things. So let us explain this problem in little more detail. So let me go to the thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And the nodes would be, this is the node 1, this is node 2, this is node 3, this is node 4, this is node 5, 6, 7, 8, 9, 10, and 11 nodes will be there. And since each one is of equal length, so if L is the length, then this guy, each one is equals to L by 10. So each distance, each length is equipartitioned as L by 10, because we have 10 elements. That is what has been done here. So since our NE is equals to 2, we will have total 10 into 1 plus 1, 11 nodes, and with the 11 nodes you will get 10 intervals. So total length is divided into 10 equal intervals. So that's how the coordinates are generated. And then the connectivity table for this one, for the N is equals to 2, would be for the element, this is element number, this is node 1, and this is node 2. Simply it would be 1, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be 1 and 2. This is 2 and 3. This is 3 and 4. This is 4 and 5. This is 5 and 6. This is 6 and 7. 7 and 8. 8 and 9. 9, 10. 10 and 11. This is the element connectivity table. And then, so that is what has been generated in this place using this commands. And then our integration points are, endpoints is NE minus 1. Since NE is 2, our 1-point integration scheme has been chosen. And then we obtain the weights as well as the Gauss points for the 1-point schemes from here. And then we develop the element stiffness matrix for each and every element by looping over all the elements. Now for all the elements, you obtain its local coordinates, and then here we obtain the shape functions. We have seen that when it is two-noded, then if this is minus 1 and this is plus 1, your origin would be at 0. So n1 of x or c, whatever you want to say, this is node 1, this is node 2. So this is similarly is given by so let us, the same thing has been coded here. So 0.1/2 into 1 plus c at the corresponding integration point, and then if you differentiate these things, dn1 by xc is equals to minus 0.5, and I differentiate this with respect to this, and similarly dn2 by dxc is equals to plus 0.5. This is the thing. So once you have that, then you obtain your dx by dz. So that to do that, what we have is, since we know that x is equals to xi ni by isoparametric formulation. So dxi by dc is equals to xi into dni by xc. We already know these things for 1 and 2, and we already know the coordinates. Let me see the coordinates. Let me write down the coordinates for our case. The coordinates are, and node number, node versus the thing. Node 1 is 0, node 2 is L by 10, node 3 is node 6, 7. Node 11 is L. 10 into L by 10 is L. So the total length, this is L, is nothing but length. So this is our nodal coordinates. So for any given load, let's say for this element number 3, this is element number 1, this is element number 2, this is element number 3. So let us say if I want to do for element number 3, so for element number 3, the local node 1, local node 2 are nothing but global nodes 3 and 4 for a element number 3. So for x of 3, so this is x3, this is x4, is 3L by 10. So we know the things. So we know these local things. We know this thing. So we can obtain that. But we are interested in obtaining dc by dx, which is 1 by dx by dc, which we obtained through this thing. And then when we want dn by dx, dni by dx, it is dni by dc and dc by dx, which you obtain from this. So that's what has been coded in here. So since with respect to isoparametric or the natural numbers, we know our shape functions and the derivatives of the shape function, then what we do is we'll compute the dx by dx and dn by dx, just as shown in the previous thing, by obtaining the things. And then once we know this, then we are ready to formulate our k element. Okay, so the k is done by in this manner. So for the 1D element, as we have seen earlier, the k for the any element is integral of dn by dx ae transpose dn by dx dx. But since we are doing isoparametric formulation, we have to make it as -1 to 1 dn by dx this will become j times dx, where j is equals to so using that thing, we are transforming this to the isoparametric integral, and this integral is changed into the quadrature schemes, and I is equals to 1 to some endpoint quadrature scheme, and let us call this as a function f of c dxc. Then we'll write it as wi f of I, where I is f of xi. So these are evaluated at the Gauss points, and there is 1 to n number of Gauss points. So you can integrate in using different Gauss points. We have chosen n is equals to 1. In our case, n is chosen as number of nodes per element minus 1. So this is 2 minus 1, this would be 1, so n is 1. So let us have a look here. So what we are doing, we said this integral k is nothing but integral of, this constant is a times e, and this is the weighing function, and this is the f of function, and so we can write this thing as evaluated at xi, ae evaluated at xi, dn by dx evaluated at xi, j evaluated at xi, everything is evaluated at xi into see this is your function, so this weight is there. So this is what is your k element matrix. Because of this summation, you have to write it in this manner: k element ab is equals to constant a, this is ae, this is function, j d nx, something like that, stiffness for each and everything. Similarly, we need to also calculate the body force. As we shown earlier, the body force F body force is equals to integral n transpose b dx a to b, which again can be changed as minus 1 to 1 n transpose b dxc. So that is what again can be changed as Gauss quadrature wi this is j is missing times j. So this is the weight, this is the body force, this is the shape functions, and the j is the Jacobian that is multiplied to get the body force. Similarly, there will be another loop to add the tractional forces. So this is where you add your traction forces. Here in 1D case, the traction forces are only added on the last or the 11th node, that's the reason, or the and total number on the last node. So F node is equals to F node plus traction will give the addition of the tractional forces. Now this will give us the total thing that we are looking into, the corresponding stuff of the element stiffness matrix. Now once you have your element stiffness matrix and as well as your body forces and tractional forces, you also have to assemble them to the global stiffness matrix, and the assembly for the stiffness matrix and the force vector is done in this place. So using the connectivity, your corresponding local stiffness matrix gets added up into the global stiffness matrix. For example, in our case, our global stiffness matrix is like from degree of freedom 1 to degree of freedom 11, because we have our connectivity is very simple in this case, so you'll mostly see case. So this is what you have been obtaining, and once you obtain your global stiffness as well as global RHS vector, then you have to impose your kinematic boundary conditions, or kinematic boundary conditions are also known as displacement boundary conditions. So to impose those things, Alan has done it in a special peculiar manner. So this is different from what we have studied earlier. In these things, what he does, he plays a little trick. So what he does is, let me show what he does. So he takes, let's say, this is K global matrix. D1 is equals to 0, right? If D1 is equals to 0 and all other things are present which we don't know, right? So if everything is there, so D1 is equals to 0, D2, D3, D4, and runs to something like that. So what he takes is, he takes the first row for which the displacement is there, he takes everything and replaces everything with zeros, except the first one, he will put it as 1. He will put it as 1 and all other things as zeros. So if this one is in the first position, you have to put the 1. If it is in the fifth position, you have to put 1, and rest of the things are 0. And further, in the force F1, so he takes the force vector, the corresponding force, and he replaces it by that value. So then already that means 1 into D1 is equals to 0. That means D1 is equals to 0. If this is delta, let's say if this is delta, let's say if is delta, then he will replace this by delta. So then automatically your D1 becomes delta here. So that's what he is doing here. That's what he's imposing. He's keeping every the first row where the fixed degree of freedom is there, everything set to 0 except the first one, which is set to 1, and the corresponding force is set to 0. This is how he makes our K matrix non-singular, and now it can be invertible. And then he inverts it using LU decomposition whatever method, and then he plots it. So let us see how he has solved this problem and run it through. This is the displacement he has plotted with respect to the things. You have seen that the total length of the beam was phi, so correspondingly you can see the x coordinates are the things, and you can see 11 points. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 nodes on these things, and the displacement is kind of plotted on the y-axis, and the x is plotted on the length is plotted in the x-axis. This is how you determine the displacements. Now we can also check the same thing by turning it into a quadratic element. Let us see what happens if it is a quadratic element, and let's rerun. Let us run it again. Almost it also comes the same manner, but here this is the first element. This is the first element, right? So let me copy it and place it in our this is a thing that is obtained with respect to NE is equals to 3 and more or less same, but the way it is different. This is when it is equals to 3. So on this and element this element 9 and this is element 10, 8, 4. Node 3, node 5, and an identifier. Connectivity is a connectivity table. Connect is a connectivity table, and fix will give you total number of prescribed displacement. Fixed nodes is the listing of the fixed nodes. So first, we need to mention the node number and which component you are constraining. Is it first component? It is U component, V component, or W accordingly. 1, 2, or so that's the reason you require 3. And then similarly the load vector. In the load vector you need to say on which element this traction load is distributed load is acting, and on the element also which phase, top phase, side phase, right phase, different phases will be there. Which phase is having the traction applied on it, you have to give the phase numbers. And this traction is a 2 components, whereas in 3-dimensional it will have 3 components. So it will be deload can be run up to 3, 4, 5, which will be X component, Y component, Z component accordingly will be assumed. Now we can take several input files, but we will take linear elastic triangle dot things. Let me open linear triangle to see how the input file looks like. So this is the input file. So total number of material properties that we are listing out, or the Allen Bauer is listing out, is 3, and then in which those 3 properties are shear modulus, Poisson's ratio, plane stress or plane strain condition, depending upon that, and number of coordinates per node. That means 2. That means a 2D problem. and number of degrees of per node will also be 2, because this is 2, and then number of total nodes. This problem has maximum 4 nodes. It is a rectangular box, so I'll show you the input file later, but for now you just see. So this is the left bottom corner, this is the right bottom corner, this is right top corner, this is left top corner, and the element connectivity table is given here. There are two triangular elements, the top half of a triangle, lower half of a triangle. I'll show those things, and total number of elements is 2, and on any element it is a triangular element, so total number of nodes per given element would be 3. That's the reason you have 3 these things. Further, one thing for the element identifier, the other thing is how many nodes are following it. So these two are kind of standard, and then this is the total number. These are the node listings that connects the element. Then how many nodes have been prescribed? These nodes, at node 1 is constrained over the x and y, and node 4 is only constrained in the x direction. That has been listed out. And then how many prescribed tractions has been added, what is the phase and what is its value has been noted. So let me draw this picture for you about what is the problem that you are solving. So in this case, it is, this is your geometry, this is the node 1, this is your node 2, this is your node 3, and they are discretized using a triangular element, and the triangular element is formed using 1, 2, and 4. So 1, 2, and 4. So the element 1 is known as 1, 2, and 4. This is one element, and this is another element. So this is element 1. This is element 2. So 2, 3, 4 is the element 2. 2, 3, 4. This defines the element 2. 1, 2, 4. 1, 2, 4 defines the element 1. Okay. 3 says that total number of nodes are 3 in both the cases, and it belongs to some identifier, so that some post processing can be done. So this is, at this case, you can assume it is a dummy variable. Now on this, what we are constraining is, at this place the x is constrained at ux, or you can write it as, at the node 1 u is equals to 0, v equals to 0, and at the node 4 only x is equals to 0. That means only this component v is, sorry, u is equals to 0 at the fourth one. So this is u1 is equals to 0, v1 is equals to 0, u4 is equals to 0 are the boundary conditions. And on the second element, on the phase 1, so when for a triangular elements, the phase 1, anything that connects between the local, put local, local, local phases. So on the phase 1, attractional force of 1, on the element 2, phase 1, a magnitude of 1 in the x direction. In the y direction it is 0, so it is purely in the x direction. This traction has been applied as the boundary condition. This is the problem Professor Alan Bauer is trying to solve using this piece of input file, as well as the code that takes it is this one. So this is the input file which reads the mesh, boundary conditions, and forces, loads, and other things, material properties. So all our results will be thrown in FEM results.txt, and to read the input file uses this function. So let us go and see this function. He stores of material properties, this is across this material rocks and chord and degree of freedom and node, all the things that has been read through that has been added into these variables, and this is function calls. It will go to this file, read all the elements and stores in the corresponding variables. Now once we have this variable, this is this matrix. Yes, to run through the all the elements. So it will tell you this is a K matrix when you are seeing outside. So it has been initialized here to 0. Then you run over all the elements and you get its local coordinates. Once the local coordinates is there, this local coordinates are fed to element stiffness matrix. So L stiff is the thing that gets you the element stiffness matrix. So let's go to the L stiff and see. So once you see the element stiffness, you run over the integration points. So you loop over all the integration points. For that, you need to find what are the number of integration points. So, and these are all in. So once you get the number of integration points, for that corresponding integral, get your C and W. These are the weights, and the Gauss points has been obtained through different feed functions which are there elsewhere. So I will show you that at a later point. So now let's you for a corresponding 2D or 3D element, the corresponding Gauss points and Gauss weights, or integration points or integration weights, what you call it. And then now you can loop over all the integration points and then get the shape functions from this shape function and the derivatives of the shape functions in the local coordinates in the natural coordinate system. We don't want the derivatives of the shape functions in the local coordinate system, but we want derivatives in the global coordinate system. That means we don't need dn by dc or dn by eta. We want dn by dx and dn by dy. Now here it is 2D, two variables. Right, so we don't need these things. We need, so in order to get dn by dx, we write it dy. So, but we need to obtain these four. To obtain, we need to first get the Jacobian. So the Jacobian, and then find out its inverse. So the Jacobian is formed at this place, and the determinant of the Jacobian is also obtained at this thing. The determinant of Jacobian also he calls it as dt, or it's also equals to j, as we have always called. And then, but we are not interested in j, but we are interested in what we call it as. We are not interested in these four. Actually, we are. So actually, in order to get these things, we are interested in these things. But the so what we need to do is, okay, I think I might have just, let me write it, dx is equals to, so that is correct. So this is the Jacobian, but the Jacobian inverse is given as local coordinates, which element coordinates is already there. These are the local coordinates. These are the local coordinates we already know. So what we can do is directly compute our Jacobian here and get the determinant of the Jacobian and inverse of the Jacobian. From the inverse of the Jacobian, we are good to get our global shape function derivatives in this appropriate manner. Once we get this thing, then we are ready to obtain the strain displacement matrix. This is the strain displacement matrix. Strain displacement matrix are the functions of the global derivative functions, which is framed here. And once the strain displacement matrix are there and you have material stiffness, then you multiply your material stiffness with your strain or increment in the strain, you will get your local stress. And if you require stress, you can obtain the stress. Otherwise, you can use the same material stress Cijk by the corresponding strain displacement matrix to your K matrix. Once the K element stiffness matrix is obtained, one can also obtain the corresponding force vectors. So let us go back and like this element stiffness matrix is obtained. Once the element stiffness is a long procedure where you run over all the Gauss points to integrate K element local stiffness matrix, and then as I said, I have to just re-emphasize that what we are doing here is K element is integral B transpose dB, where B he calls at ds dE, and B is the strain displacement matrix, which is a function of dN by dx and dN by dy accordingly. To isoparametric formulation -1 to 1 plus B transpose dB. There is no transpose here. And this has to be changed as the Jacobian times dc d eta, and again these integrals are changed into sum over the integration points I is equals to 1 to integration points I is equals to 1 to n integration points, it is B transpose D, B J evaluated at corresponding xi, let's say this is J, and yj, which are the Gauss points in the x direction as y direction. So this is called n cross n point integration scheme or quadrature scheme. J is also been there. So this is how the integration has been performed. So that is what has been coded in this L stiff matrix, L stiff function, and that has been invoked, and element stiffness matrix is obtained in this. Once the element stiffness matrix is obtained, then for all the elements you need to assemble them to form the global stiffness matrix. So based on the connectivity, you develop, you try to fix. Once you are done, then you go similarly global traction matrix has to be obtained. So let us just again to obtain that. So you again run through all the number of loads and again all the number of for the corresponding loads, you will pick up your corresponding phase and element, and for those elements you integrate it again as we have seen earlier, the forces due to the traction. This is the phase. In the phase here, for two-dimensional, the phase would be a single dimension x. So again, by adapting to the isoparametric formulation, this would become J, but this J is not for the total element. This is, let's say, if I'm having a traction on this element, right? So this phase, so this take a reduced 1D element whose this thing is there, you map it this one into J. So, and this, the corresponding traction J for that, and dc minus 1. Again, this can be replaced as Wi n transpose Tj. I forgot something here. When I just try to do it, I have to multiply the weight Wi, right? So weight just to be multiplied. Like this, I've shown it there, but I forgot to put it at a previous place. So this is what has been coded in this. And then it has been assembled vector, and then we head back to the where we were. And then you apply your kinematic boundary conditions of the displacement boundary conditions. Just I set everything, then the entire row, whichever you know, to 0 except the diagonal 1. Set the corresponding diagonal entry to 1 and change your force vector to the actual displacement which was imposed. That will automatically make your K matrix KUU, and as well as other things are, and it also makes our K matrix non-singular so that you can invert it. Once you invert this with respect to force vector, you get your degrees of freedom U, and then you can go ahead and post process it for plotting. as well as to see to compute the stresses, for reaction forces, and other things. So let me run through this file so that you can understand. So this is the file, we have run it. This is the initial mesh. This is the initial mesh, and then the initial mesh and application of the traction forces. The red color is the deformed configuration, green color is the undeformed or the original configuration. This is undeformed configuration, and this is deformed configuration. So this is how the displacement looks like when it is plotted for the triangular element. So similarly, let us try to run through some other examples. So single brick element. So let us see the input file once. So again, it has two material properties: shear modulus and Poisson's ratio. Number of coordinates per node is 3, so it's a brick element. So let's not solve the 3D element. Let's do a 2D element first. I will come back to the 3D later. So let's do quad, which is a 2D thing. So let's solve the quad 4. So again, shear modulus, plane stress, plane strain, 3 material things, 2 degrees of freedom, and hence 2 degrees of degree of DOFs, as well as coordinates, x and y coordinates of the nodes, and the connectivity table. Since each are our quad elements, so that means 4 nodes will be there on each of these things. This is your corresponding 8 elements are there on the things, and there are 4 things that are kind of constrained. That is, node 1 is constrained at x and u and v. Node 6 and node 11 has been constrained for the thing. So let us run through this code. This is our initial mesh, and this is the initial mesh, and the final mesh is superimposed. So let us again here. So the node numbers were done in this case like this. This is node 1, node 2, node 3, node 4, node 5, This is 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Here we imposed u1 is equals to 0, and v1 is equals to 0, that is, it has been constrained both in the x and y direction, and whereas this is only imposed in the x direction, so u6 is equals to 0, and u11 is equals to 0 are the kinematic boundary conditions. And then on the element 4 and 8, on the second phases attraction along the x direction of a magnitude 1 has been applied. That boils down to, on this, we applied attraction on these two elements. This is element 1, element 2, element 3, element 4, element 5, 6, 7, 8. This is phase 1, this is phase 2 for this element. This is phase 1 and this is phase 2 for this element. So on the phase 2, attraction of 1 in the x direction has been applied on the 4th and 8th element second phases as the boundary condition that resulted in the deformation of this red thing. So this is deformed and the green color is the undeformed configuration. So this is how we have solved these two problems. You can run through it. I will not show all the things, but I will quickly run through other things before I break for the day. So let us quickly run a 3D problem with a brick element. So this is the 3D element with a single brick element. I hope now you can see this is the brick element. So you have 8 brick elements using 8-noded brick. 8-noded brick means each cube is a brick element, and each brick has 8 nodes. And let us see so the material properties are shear modulus and Poisson things, 3 degrees of freedom, and 3 nodal coordinates, and these are XYZ coordinates. Total nodes are 24, and the total elements are kind of 6. And this is the element connectivity table, and each has 8 nodes that are connecting the brick element, and these are the degrees of freedom which are fixed in 1, 2, 3, and other dimensions. And these are the attraction forces on the element 3 and 6 on the phase 4 along the x direction. Attraction of unit has been applied, and this is the problem that has been solved. So this is for the 3D problem. So this is your x direction. This is your y direction. This is your z direction. Your node numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and on these are elements. This is element 1, element 2, element 3, element 4, element 5, and element 6. On this element, attraction of on this face, traction of 1 in the x direction has been applied, and so all these nodes, node 9, 13, I think I made some error in numbering it, so let me just see the numbers. Forgot to put it. Okay, sorry, this is 13, this is 13, 14, 15, this is 16, this is 17, 18, 19, 20, this is 21, this is 22, 23, this 24 is the thing. So all these nodes has been constrained for the x direction. So if you look at it, if you look at n fix, so all the node 1, 13, 5, 17, 21, 9, one, 9, 13, 21. By 9, 13, and along x direction, node 1 and node 13 are restrained against the 2 direction. Node 13 is this one, is constrained along second direction, and 1 is again constrained along the third direction. So this is z constraint, this is y constraint, value problem it has been shown, and this gives you the red color graph, gives you deformed configuration was the undeformed configuration. So with this, we have showed 1D, 2D, as well as 3D codes. Next time what I will do is I have to still show some elastodynamics as well as mode shape problems, but I haven't given you the theory. So in the next class, I will cover those two, and then I will show you a couple of codes. So if you have any questions, please stop me and ask.